to the cloud. Then, okay, and Peter, you can take over whenever you're
Okay,
ready.
great. Thank you. I'll just.
Oh, I need to allow you to share screen. Yes.
Right. Oh, right.
Go
Okay.
ahead.
Let me see. Where's it gone? Trying to find my. There it is. That should be. Let's see. Is that picking up the right screen? Do you see response deficit analysis?
Yeah, we see the screen.
Yeah.
Yes.
We see the screen. Okay, good.
Okay.
So yeah, response deficit analysis. So my presentation today is going to be on this technique of analysing wind turbine operational data to track trends and variations and deviations in performance. And so the data set that was provided for this challenge, you know, I've used this technique on that to see, does it tell us anything? So I'll get onto that towards the second half of my slide set. The first half is really what is response deficit analysis. So yeah, what is response deficit analysis? So we'll just take it one word at a time. Response. So by response here, we mean the way in which one parameter will vary in response to variations in another parameter. So, you know, that could be, for example, power output varying in response to variations in wind speed. Or you could think of the relationship between wind speed and blade pitch, or another kind of response that might be considered would be the way that the drive end and non-drive end bearing temperatures of on a drive shaft vary in relation to each other. You can see how one relationship is likely to occur when everything's healthy, but if maybe the shaft is misaligned or the lubricant is contaminated for one set of bearings because of degradation or whatever, you know, that relationship could change. So something that characterizes that relationship and allows you to track any changes in it would be useful. Similarly, another one might be flapwise blade root bending moment related to wind shear, and so on. In general, any kind of relationship could be considered when using this technique. What we're going to think about is a power curve, the relationship between wind speed and power. That's the data we've been provided with. So we'll look at power curves. What do I mean by deficit? Well, you can have a baseline or a reference for the relationship you're talking about that you want to evaluate other examples of that relationship relative to. So that reference, that baseline that you're going to use to look for deviations could be something like the warranted power curve, or it could be an observed power curve that you observe during what you consider to be normal operational conditions. Or it could be some kind of park reference. It could be like a kind of consensus wind turbine power curve that's, you know, the average of all turbines in the wind farm or something, kind of like a similar to consensus wind direction, but like a consensus power curve for the park. You could use that as a baseline. Or if you're tracking things varying over time, you could choose a period of time that you are going to use as your reference. It could be a power curve test, a formal power curve test. It could just be whatever you observed shortly after commissioning, so that you can track any changes relative to that. You determine what your baseline performance is going to be. And then you look at a deficit. What do you mean by deficit? We mean, well, a difference between what you observe and your baseline. So looking at the data set that we've been provided with, looking at the turbine upgrade data set pitch angle pair, we on this occasion I've chosen as my baseline just the sum total average power curve, just taking all data. Yeah. So the observed power curve overall data. And then in this plot here, I'm just looking at the data for the test and control turbines, because in this data set, normalized power is provided for a test turbine and a control turbine for comparison. I'm just looking at the data where the wind direction is in direction sector 8, so sort of south-southwest. And I'm just looking at the month November 2010. And I get these results. The grey dots are the test turbine data. The solid green line is the baseline for the control turbine. The solid red line is the baseline for the test turbine. So when, for that month, I subtract the observed power curve for the test turbine for that wind direction sector and that month, I subtract it from the baseline, I get that dashed red line. That's the test deficit curve. And then the corresponding deficit curve for the control turbine is shown in the dot dashed line as well, plotted against the right-hand axis. So power plotted against the left-hand axis for the power curves, deficit plotted against the right-hand axis for the deficit curves. So that's great. So what do we do now? We want to analyze this. So what we do, we've got this deviation that represents how the observed response curve, in this instance a power curve, differs from the baseline that we've chosen. Why would we analyze it? Well, deviations will occur naturally anyway. Operational conditions vary in a perfectly natural way, resulting in perfectly normal deficits that are to be expected. You know, the power performance of a turbine varies under different conditions of wind shear, turbulence intensity, and so on. So we'd expect deficit curves to vary as those conditions vary. But the deficit curves can also vary in other ways due to other causes that are a reason for concern. You know, abnormal or delinquent power performance that's due to maybe an incorrect control setting. You know, maybe causing a yaw misalignment, a pitch misalignment, a premature cutout, or a delayed cut-in of the turbine. Or you could have damage, component degradation, causing a deterioration in the performance. Maybe you can detect the signature of an incipient failure in the analysis that allows you to intervene prior to an actual component failure that would incur a greater cost. In general, different kinds of component degradation result in different kinds of deformation of the response curve, resulting in different shapes of the deficit curve. So if we can characterize those different shapes of the deficit curve, can we pick out deficit curves that are normal and not a cause for concern, and deficit curves that are something that should alert us to a need to inspect and intervene and potentially repair or replace a component? So that's what we do with the analysis. We characterize this deficit curve so we can observe trends as those characteristics change. We calculate performance metrics. So we've subtracted the observed response curve from the reference in order to obtain a deficit curve, and then we statistically characterize that curve. And there's a limitless number of ways that you could characterize that. So, typically I've used the deficits as weights to calculate the moments of the deficit curve by using them weights in the weighted average of wind speed squared or cubed or raised to the power 4 to give a metric that is indicative of something like the variance or the skewness or the kurtosis of the deficit curve. And then those are numbers that I can plot in a graph. What I do is I take my data and I can aggregate it into data sets according to different criteria, and then calculate those metrics for each of those data sets. So I'm dicing my data up into potentially different periods of time for the same turbine to look at how the metrics change over time, or maybe dividing the data up by turbines for the same period of time to look at the variation in performance across a group of turbines at the same period of time. Or I can look at different direction sectors because the terrain will influence the conditions that the wind turbine encounters, which then will be reflected in variations in performance. And so I can see the effect of some turbines being exposed to more higher shear or turbulence relative to others as a result of the influence of the terrain. Once I've calculated these metrics, I can pair them up to plot them on a graph to provide an immediate visual representation of this variation in performance. And this is really where the power of the technique comes from. It provides a simple at-a-glance summary of the variation in performance across a large group of situations. So each point could be the performance of an individual turbine during a particular month of operation. And you could take a whole wind farm with turbines and years worth of data and push it through this analysis and generate one single plot with points for each turbine and each month. And you can review that to really support your O&M triage, allowing you to inform how you prioritize inspections and maybe alerting you to things where an inspection should happen sooner rather than later. So this is an example. So here we have this plot, and we have two metrics calculated by turbine and month. So the different turbines are color-coded, and for each turbine, the calculations have been performed on a monthly basis. And the pairs of metrics for two of these metrics, I'm calling them M3 and M4. So, broadly speaking, a kind of a skewnessy metric and a kind of a kurtosity metric for the deficit curve plotted against each other. And we can see that we've got this kind of group of dots down here at this wind farm. And we call that the main sequence. Now, if the performance corresponded exactly to the baseline, that would generate a point at 0, 0 on this plot. But as we've observed, performance will quite naturally vary as operational conditions vary. So really what that does is that kind of smears normality out from the 0, 0 point out along a line corresponding to the normal variation of operational conditions and the normal response of turbines to that variation. So that's the main sequence. That's what 1 point on that there corresponds to that power curve, which is the power curve for one turbine for a particular month of operation. Then we have all of these anomalous outliers. So straight away, this is what I'm saying. It's a visual representation. Immediately, you know there's something wrong with all of those turbines for all of those periods of time. And you want to, from a triage point of view, that's where you want to look and investigate in more detail, to drill down into the data, look at the event logs, and so on, and find out what was going on. So this is a rather extreme example just to illustrate the point, but you can see that there's something badly wrong there, some crazy curtailment happening. This is a real world example, and this really weird behavior wasn't expected. So so this really did prompt some further investigation, and it was costing a lot of money. So that's essentially the analysis. And as I say, the deficit will vary between individual turbines in a fleet. So you can use this technique to look at maybe the impact of differences in O&M strategy across a fleet, or between different operational periods of time for an individual turbine. So you can track variation and deterioration over time for that turbine, or between different direction sectors for a turbine. As I've mentioned, you can look at the way the terrain influences the wind conditions at the turbine and how that varies with wind direction. How do you calculate them? The performance metrics, as I say, there's an infinite variety of metrics that you can calculate. I'll show you a couple of examples in a moment. But the reason to have a variety of metrics is because, as I've suggested, you can sort of decompose the deficit curve in different ways using different metrics. There are metrics that will be more sensitive to the skewness of the curve, and metrics that will be more sensitive to the kurtosis of the curve. Different kinds of shape will have a stronger impact on different metrics. And so, well, different kinds of anomaly, performance anomaly, results in different kinds of deficit curves. So, for example, if you have a pitch angle, pitch regulation fault, just you get a kind of a flattening in the power curve between where you have the point where the blade starts to pitch up to where the knee is. You kind of have a flattening out of the knee, so that gives you a kind of characteristic deficit curve, which maybe a skewness type metric would be more sensitive to. You can use these, as I say, use these different kinds of metrics to try and pick out different kinds of shape in the deficit curve. So looking at the data set that was provided, this data set, there was wind speed, air density, normalized power, provided for a test turbine and a control turbine from April 2010 to August 2011. And we know there was an upgrade, or there was some change made around the 20th of June 2011. Now, what I did was I density corrected the wind speeds and then pushed the data through this response deficit analysis to see if that event, that change, was reflected in the analysis. So what I did was I aggregated the data by month, so I could track variations in performance over time, which is what we're interested in here. And also I broke it down by wind direction sector, because I noticed that, you know, there are some directions where one turbine is obviously in the wake of another turbine, and other direction sectors where that's not the case. There are some direction sectors where there's not very many counts, not a lot of data, other direction sectors corresponding to the prevailing wind direction where there are many, there's a high data count. So yeah, that was the kind of data coverage that I observed there. You can see that for no given month do you get close to 100% of the possible data. The coverage is quite variable from that point of view. And then within each month, you can see that in general, Sector 8 and Sector 9 are the most common from a direction point of view. So what I did was I calculated my performance metrics. So when doing this, I'm calculating over a range of wind speeds. I've mentioned using the deficits as weights in a weighted average of the wind speed, or the wind speed raised to a given power. So you do that you predetermine what range of wind speed you're doing that. So we've went from a low of 3.5 meters per second up to a high of 13.5 meters per second, with a midpoint of 8.5 meters per second. And then these metrics are what I calculated. I took the wind speed minus the midpoint wind speed as my wind speed signal, and then just calculated weighted averages of those, weighted by the deficit, raised to the power 2, 3, and 4. Normalized it by the midpoint wind speed raised to the same power to keep them all roughly the same order of magnitude. And so when I take the test turbine data for Sector 9 and I calculate that for each month, this is what I get, plotting M3 against M2. The last 3 months of the data set have got little circles around them, just those ones there correspond to the last 3 months when we think something is happening. And then that's the same calculation, but for the control turbine, just looking at Sector 9. So what I did was I said, well, what's the distance between the test and the control turbine metrics? How does that vary with time? Essentially, how like the control turbine performance is the test turbine performance? And using as a measure of that the distance between the points representing the performance of each of those turbines on that metric plot. So that distance there. So how does that change with time? you can see that there, and this is where we think there's some upgrade or some change that brings the test turbine more in line with the control turbine when that distance is small. Did the same analysis with sector 8. There's another sector where there was a lot of counts. So again, you can see the test turbine data in red X's, control turbine data green plus signs. The last 3 months of the data set, I put a circle round. This is metric plot M3 against M2. And again, the same analysis of the distance between the points on that metric plot for the test and control turbine. So again, it really drops off there at the very end of the data set. It really becomes quite small. And then just, to illustrate that you can use all sorts of metrics here. This is M4 against M3. And again, similar picture using those metrics. So really, that concludes my presentation of response deficit analysis. I want to just wrap up by saying, well, what could I have done differently in, exploring this space, exploring this method of analysis? I could have chosen different baselines. So it's pretty crude, me just taking the whole data set and just, lumping in all of the data from the period of time that maybe one might legitimately consider a baseline, along with the period of time where there's some anomalous performance potentially that I'm interested in looking at, and just lumping that all together and calling that my baseline. That seems to be a little bit indiscriminate. It might make more sense when tracking changes over time to choose just the very early period of the interval of time under consideration as the baseline and use that. That might be a more sensible baseline to use. You could use different data aggregation. Really, I think that's determined by what question you're trying to answer. I think for this one, grouping the data by turbine, month, and sector made sense. Different questions might suggest other subdivisions of the data for this kind of analysis. Another thing I could have changed was what my low, middle, and high wind speeds were for the range over which I was performing the calculation of those metrics. I could have calculated different metrics. As I say, there's an infinite variety of metrics that you can calculate to characterize these deficit curves. So, for example, one that I've used in the past is where you calculate these sums, Sn, where n is just the difference, your wind speed measure, your distance of your wind speed from the midpoint of your analysis, raised that power, weighted by the deficit, and then calculated metrics by taking ratios of those different sums, and raising one to a power relative to the other in order to try and get them to normalize out, to be dimensionless, and come up with metrics of a similar kind of order of magnitude and size. So you don't end up like plotting 1,000,000 against 0.01, that kind of thing. And then also more sophisticated metrics where you combine different powers of that velocity signal in that way. As I say, the scope is wide open. So that's everything I have to say about response deficit analysis.
Thank you very much, Peter, for a very interesting presentation. We have about 25 minutes left for discussion, and I'd like to open the floor for if anyone have any comments and questions for Peter from the audience.
Yeah, I have something. This is Akshay here. Hi.
Please.
So, Peter, I was curious about your experience with the relative sizes of the data sets themselves when you're segmenting them, as you said, by turbine, by month, by sector.
Yeah.
And how much does that influence this deficit as a statistic? I mean, is it sort of statistically
Yeah,
consistent, very
yeah, I
sensitive
think
to the
so.
size?
I think that's a really good point. So if we, if we go back to, if we go back to, what was it called? The data coverage. Yeah. So, you can see once you start breaking things down by month and by direction sector, you can see for some of these cells here, the data count's going to be pretty low. So the statistics that you can calculate are not going to be terribly robust. So I think that is a very key point as you think, well, something like a month for one turbine, taking data for something, something like the prevailing wind sector, or if you're doing it, if you potentially vary the size of the direction sector you're considering to try and get enough data that you'd get a reasonably robust calculation of your performance metric. Yeah, I would say I probably wouldn't want to go actually much lower than a month. Just in terms of the, I mean, let's see, I've actually got the, yeah, let's see. Here's a pull this over here. Let's see if I can pull this over here. Here's a spreadsheet with some of my calculations in it. And yeah, so you can see I've got sector 9 there on June there. So that's sector 9 in June. That's 255 data points have gone into that calculation. So, that's giving me 255 points to calculate an observed power curve here. Yeah. For comparison with my baseline here, to get this deficit here that I can use to weight the averages of the wind speed squared and cubed to get my metrics up here. So yeah, you can see how, the robustness of this power curve, and hence the robustness of that deficit curve, is going to deteriorate if you start going down to less than a few hundred counts, in terms of the data. So in my experience, you get that, if you say a period of time, a month is a good period of time to try and get enough data to plot a power curve, yeah, to then get a deficit curve. In terms of the sheer volume of data that you're pushing through the analysis, you can see that I've done this in a spreadsheet because it's a relatively small data set, yeah. 2 turbines at roughly a year's worth of 2 turbines. When I've done this in the past, though, where we've been, where we've been working with a kind of a commercial performance monitoring platform that's implemented this kind of analysis, and it's been used to monitor, large wind farms. Yeah, we've not used Excel for it. We've implemented it with a relational database, performing queries against a relational database or something, MySQL or something like that.
Right.
So, and then, I think, then, if you're, if there's like a gigabyte of SCADA data that you want to push through the analysis, clearly you can't do that in a spreadsheet. You have to do that in something like a database. But yeah, those would be my 2 points. Would be the robustness of the statistics requires a certain data count. So, like, roughly kind of a monthly analysis is I think good for that. And then the sheer volume of the data that you're pushing through the analysis will then determine how you actually implement that in terms of performing the calculations. Yeah.
And a quick follow-up will be, I mean, the deficit calculation itself, is this directly from the raw data, or is there a model involved? fitting
There's
or
there's no
a
model involved.
regression. Okay.
No, there's no regression. There's no model. It's directly from the raw data.
Okay.
Simply it's effectively a statistic that's calculated on the basis of the raw data.
Directly on the yeah.
Mm-hmm.
And
Yeah,
I mean then perhaps the calculation itself can give you a good idea of say the sampling bias or
yeah,
the uncertainty with this kind of bootstrap approach.
yeah. So there you can see the calculation itself. There's a power curve for that sector in month for the test turbine. There's the baseline. It's calculated over all data. There's the deficit, which is just the baseline minus the minus the observed one. Yeah, that's just wind speed minus the mid wind speed squared or cubed, and then the metrics here are just, you can see it's just some product of deficit times that.
Right.
Yeah. So, but as I say, this is really because that's something that's very simple to implement in a spreadsheet. My point would be about the metrics is that it's very flexible. You can calculate these metrics if you want, or you can go and devise your own metrics that are more sophisticated if you want. I mean, the sky's the limit when it comes to what performance. So I think in terms of the kind of investigations that are worth pursuing are things like, well, what metrics do I actually find most useful? If you're monitoring lots of turbines, try out lots of different metrics. You'll find out which ones are maybe most sensitive to different kinds of performance anomaly. Like as I mentioned, some metrics might be better at finding the pitch regulation problem. Other metrics might be better at finding the premature cutout, that kind of thing.
Thank you.
Any other comments and questions for Peter?
Can I add something?
Please.
Yeah, first, thanks, Peter, for an interesting presentation. I think it's a very interesting method, and I think it makes sense to know that different types of deviation, natural or by some real performance issue or upgrade or whatever, have different kind of signatures with wind speed, for example, and that could really help to separate out these different influences. One thought I had just now is, have you explored at all, once you've gone through these different investigations, whether you can sort of derive a bias function or something like that, something more a bit more sophisticated than just like a simple bias correction, if you could derive something based on these statistics. I suppose this might be difficult, but and of course the higher you go in terms of statistical moments and so, the more sensitive they will be to scatter and so. But if you have any thoughts there, that would be interesting to hear.
Yeah. I mean, I think there's a short answer. I think there's still a lot of work to be done in investigating the potential of the technique. The reason why the answer is no is because the original motivation was really all about that O&M triage. The original motivation for this technique was being able to take a large volume of SCADA data, push it through an analysis that that was completed in seconds, and immediately be able to say, good, not good. And the idea, so the initial motivation was that really the kind of analysis that was being supported by this technique was actually the kind of the human domain expert. It wasn't really developed to fully automate anything. It was actually developed to let the domain expert very rapidly find where they could most effectively spend their time looking. So that the domain expert would immediately, a few seconds, they'd pull up this plot, and then they'd know, right, those turbines during those periods of time are the ones where I should really focus my attention. So it was the original motivation was about triage. Yeah.
Yeah, makes sense.
You know, so the additional issues, these are additional statistical issues, remain largely unexplored. Yeah. So yeah, as I say, I'd be keen to spend more time looking at that, to be honest.
Even if one could build a sort of understanding of what these different statistics mean and what kind of benchmarks of, like, once you see this pattern, then, because obviously a domain expert can look at this power curve and say, like, when you see that one on the right, you kind of have an idea that there's some kind of strange derating or something going on.
Exactly.
Because people are used to looking at that, but I guess this higher order statistics people are not used to looking at, so it's not immediately obvious what the patterns mean.
Yeah, exactly. It sort of reminds me of that scene from The Matrix where he's looking at the Matrix on the screen and he goes, you know, blonde, brunette, redhead. You know, it's sort of it's about trying to make the domain expert get to the point of identifying the blonde, brunette, and redhead as quickly as possible, I think. But as you say, yeah, the domain experts that have used this approach, they do get to a point where, yes, they can pull up the power curve for the anomalous point and immediately go, that's a premature cutout, that's a pitch regulation fault from looking at the power curve. But it's interesting when they get to the point where they can say, well, in amongst these anomalies on this plot for these metrics, I recognize that I think that might be a yaw error, you know, I think that turbine there might be getting exposed to very high shear in that one direction sector. And then they go and look at a map and they see that the terrain is mad, you know, in that direction. So, but as I say, that human pattern recognition, is not something that is terribly easy to automate. And it would be interesting to look and say, well, can we develop a set of metrics that move the analysis that we're automating closer to that level of pattern recognition? But as I say, that is work that has not been done.
Peter, I have a few questions, if you don't mind. The data set you call the WDW, is that the data set we provide?
Yes, it is.
Is there any reason you call it WDW?
We do wind.
Oh, we do wind. Okay, I see. I try to understand the acronym. Okay. In that data set, when you identify the upgrade, because that data set particularly was simulated data set. When you identify the upgrade and toward the very end, and the difference between the control turbine and the test turbine getting smaller, that seems kind of different from the simulation, because the simulation, the control turbine and the test turbine was not exactly the same, but they are identical turbine, they're getting into the service at the same time, so they are very similar. The artificial simulation being injected to the test turbine is making it more different from itself, therefore it's more different from the control turbine.
Yeah. I did actually have a question about that, because when I was looking at it, I was thinking, where is it? I was thinking, why does the control turbine not? So the control turbine has got poorer power performance than the test turbine overall. That seems it seemed to me that that's the wrong way around, isn't it? Shouldn't the control turbine if we're simulating a test turbine that's got something wrong with it that then gets corrected.
No, in this particular case, the choice of the control turbine test turbine pretty arbitrary. They just
All right.
selected the closest two pairs of turbine, right? They are really kind of just like 250 meters apart from each other, probably 300 meters. So they are close enough. And also they selected two of the same type of manufacturer, the OEM, same model. They get into the service the same time. So that way, people can reasonably argue these two turbines by that time when the data was collected, they deteriorate also similarly, not exactly the same. And therefore, you can inject a difference on one of the turbines to make it more different from itself, right? For example, here, for the test turbine, there's not only one degree of change being made, there's a multiple degree from very small percentage to reasonably large percentage. So when you analyze this one, did you choose one of the column or you choose all the multiple columns to do the analysis?
I chose I chose the last the Y test and the Y control. The Y test normalized, Y control normalized, and I chose them, and then I took V and density corrected it by rho for my wind speed.
I'm sorry. Are you using the pitch adjustment data set or use the VG upgrade data set?
The VG pair. Yeah, VG pair.
Oh, you use the VG pair. I'm sorry. Oh, this is only one part of that. Right. So in this particular case, yeah. So it's also curious because in that case, we don't really know the underground truth. It's at this moment onward, and a set of vertex generators was put on the blade of the Tesla turbine. And they basically want to know, how much effect that VG will have in terms of improve the performance of the Tesla turbine.
Yeah, so this was why I had this question about the fact that the control baseline is performing less well than the test baseline when it should be the other way around.
Well, they don't. I'm not really sure how exactly they selected the Tesla turbine, and for this one they put on the VG. But my experience is that's commonly happened. They just choose one of them and put on the VG over that. And but in the conclusion, if the VG really bring the Tesla down to the control, that means it doesn't really make much improvement. Is that right?
That's what these results suggest.
Okay. You probably, when you have time, maybe just out of curiosity, you can apply this analysis to the pitch angle, because the pitch angle, how much improvement being made is artificially made.
Yeah.
We know exactly the underground truth, right?
Yeah. Okay. So, I'll try this with the pitch angle data.
Yeah. And now you can select a specific column. Because that column we know the numerical one, right? You mentioned that when you do the analysis, you use a spreadsheet, right?
Yeah.
Okay.
Because it's small data set.
Right. Do you mind sharing the spreadsheet with me, and I can ask my graduate student take a look at that?
I'll
can learn from that.
So I'm just looking at the pitch angle data. I'll look at that later. Yeah, I'll try it with the pitch angle and I'll send you the spreadsheets.
Okay. And actually, with your permission, I even like to put your spreadsheet in the workspace, and not only. Is that okay with you?
That's fine, yeah.
Yeah, okay. So that way, all the people access the workspace and in the group, and they can play around with their analysis and understand more and learn from it.
I apologize for the fact that the spreadsheets they're not really, sort of that neat.
Oh, that's okay. You provide whatever you can provide, right?
I mean, the spreadsheets that I pulled together, I was just thinking in my own head,
right,
rather than preparing something for distribution. So, apologies in advance if it takes people a bit of time to.
But that's always the case when you kind of prototype, right? Otherwise, you would never get anywhere if everything had to be like ready for production by the time you're just playing around.
Yes, exactly. So it's a playing around spreadsheet.
It's
So that caveat
yeah.
that it's a playing around spreadsheet.
Right. Actually, Christine is leading effort to like the open data, open code. I think you open your code is the very first step, right? You're not really guaranteed to open an easy to use code. We only ask you to open code. We're not really asking you to open commercial ready.
Yes.
Yeah, right. Yeah. I understand that part. Another thing, I'm sorry. There's something I wanted to say. Just yeah, sorry, I missed that. For whatever reason, I forgot the last point I want to ask you, but yeah, that's okay. And any other questions or comments for Peter's presentation? Oh, yeah, I recall what is the question. Do you have any publication related to response deficit analysis and like
Yeah,
a journal conference?
just like a couple of like Wind Europe posters and you know, presentations. Nothing any more sophisticated than what I've presented today.
Oh, okay. All right.
Mhm.
Okay. So any other questions and comments?
I have a question, Professor.
Yeah, please.
Basically, based on Peter's analysis, I realized that after the adjustment, the test and control turbine are behaving almost the same, but before the adjustment, there is a lag. If we really take when I performed the side-by-side comparison, I think side-by-side comparison was calculating the cumulative effect, both the differences after change and before change. For VG, it was around 0 and 1%. So it was very small. So I think side-by-side comparison also realize that these test and control are almost the same after adjustment, but I really don't have the intuition on before the adjustment, which one is actually doing better or that part is a little bit unknown for me. So in this plot before the upgrade, the test turbine is actually producing more power.
Yeah, I think so. When you look at the power curves for the test and control, calculated using all data, the test turbine is performing better.
I see. Thank you. I will try to take a look at it with side-by-side comparison to see if they have line outputs or not. Maybe we can discuss in one of the next meetings.
Yeah.
Thank you.
Okay, so that pretty much conclude our today's meeting. And for July, Eric Simley agreed to present his part of the work, and may not necessarily using this particular set of data, but the generally related to the topic. And in August, we have another speaker lineup for that one. And now around sometime around that time, we need also decide, you know, do we have enough interest and energy to go on beyond August? And now what time would be the best to meet? Because for the Enreal colleagues, and they would like to meet a little bit later, right? Because 9 o'clock my time is 7 o'clock their time. It's a bit too early. So they would like to push that to like 10 o'clock my time, which is fine with me, and 8 o'clock their time, which 10 o'clock my time is going to be like 4 o'clock in Eastern Europe, I mean, in the Central Europe time. And but we'll come to that point probably in July's meeting or August meeting. And with that, and thank you very much for all of you being here today, and for a very productive discussion. Thank you.
Great, thank you.
Thank you very much.